So light is an important part of many technologies. The handling and manipulation of light can be done in many different ways. Traditionally, you would do this using fixed elements such as lenses or mirrors or even optical fibres. What we're working on is developing new ways of handling light. Laser writing involves the focusing of short pulse lasers inside materials using a high numerical aperture objective lens. The high intensities at the focus of this laser can modify the properties of the materials, for example, increasing their refractive index. In doing this, we can use the laser to write three-dimensional optical circuits, rather like creating optical fibres in 3 dimensions within a block of glass. This is opening up a range of new applications, for example, in optical communications or quantum technologies. So the key technological advance we're working on is adaptive optics. This enables versatile fabrication to compensate for the effects of high refractive index materials, such as even crystals such as diamond or sapphire, and also for complex shapes and complex surfaces such as those you find on optical fibres. These same adaptive optical elements can be used for versatile beam control, such as focal shaping, or for parallelization, in order to enable new functionality in our fabrication processes. These aspects will be vitally important when moving this technology into the area of commercialization.
Until now, there are about 2 major methods that the industry has been using to produce this kind of waveguides. The first one is so-called the silica on silicon, which is also short for SOS method. In this kind of method, that a lot of waveguides can be produced at the same time, but the whole design and proceeding time can take about several months. It's a very long time. And most importantly, it can only create those waveguides with rectangular and cube size of the cross-section. There's absolutely no control of the 3-dimensional cross-section on the waveguides. The second method is using the ultra-fast laser to write those kind of waveguides inside the glass sample. And the traditional method that the ultra-fast laser has been using, one of the biggest problems is that precision is not very good. Especially on the direction of the laser propagation, the resolution can be as large as above 8 micron, which is very huge for the quantum chips or photonic chips. So in our technique, we have advanced this kind of precision into much smaller level. So we can create those optical waveguides with a precision in the level of several hundreds of nanometers. So this has been the first demonstration of this kind of ultra precision. At the same time, the optical waveguide we created using our technique has much more advantages over those 2 traditional methods. And it has very low loss, both the propagation loss and also the coupling loss, and it can be ultra-precisely control the 3-dimensional cross-section shape and sizes along the waveguide. One of the biggest advantages of our technique is that the cross-section can be made in any shape, and at the same time it can evolve along the waveguide. It can change as many times as we want along one waveguide. So we think that this kind of capability has never been demonstrated in any other technology or any other waveguides. It can be very powerful in terms of controlling this kind of different shapes with low resolution, such as low as several hundreds of nanometers. And at the same time, we found that the evolution of the shapes does not introduce any additional propagation losses to the overall waveguide. The second advantage of our technique in a waveguide is that the waveguide itself has a very low loss, both the coupling loss from optical fiber or coupling to a chip, and also the propagation loss along the waveguide. For example, for this kind of 3 centimeter long chip of the waveguide, about more than 90% of the light can be coupled in and detected from the output. And there's very little loss from the overall propagation and also the coupling. And this is very important for us to apply this kind of technology into the quantum chips, because inside most of the quantum chips, the overall loss from the coupling and from the propagation has been a big problem for most of the researchers. The third advantage of our technique is that it can produce those kind of waveguides with a very fast speed, such as this 3 centimeters long waveguide. It can only take about 2 minutes to finish the whole fabrication.
So there are applications of these technologies in ion traps for quantum computation. Traditionally, you would use optical fibres to do this type of light coupling, but the optical fibres are too bulky in order to achieve the performance we need. Even laser-written waveguides, written in the conventional sense, cannot provide the performance we require because of the refractive index change we can create is too low. Only using the adaptive optics methods can we control the light carefully enough in order to enable the correct size and refractive index profile of the waveguides to achieve the low crosstalks required in these applications. Aside from the work described in this paper, which will help photonic applications such as quantum computation, we've also been applying the same adaptive optics laser writing technology to other areas, such as, for example, the fabrication of electrodes inside diamond, which has applications in radiation sensors, or the creation of single-mode waveguides inside sapphire-based optical fibres, which we are also using for sensing in extreme environments such as high temperature. We can also use the same technology for mode converters for chip-based quantum light sources. The biggest problem here is the mismatch in optical modes between those chip-based sources and optical fibres. By using our adaptive optics beam shaping methods, we can create better mode matching and hence reduce the losses involved within these systems. In this particular case, we've been able to improve the coupling efficiency to 30% compared to the previously achievable 10% using more conventional methods.
Our mode converter or waveguide can be very compatible to the single mode fiber. This is one of the very big advantage to be used in a lot of chips. Such as we found that the overall coupling loss between a single mode fiber to our waveguide is only about 3%, which is very, very low, even lower than some very industrial standard the fiber coupler. So we think that this is a huge advantage of the waveguide to be applied to most of the integrated circuits. Well, we also find that our waveguide can also be used to even control the light polarization. We found some very interesting behavior that the overall perpendicular polarized light passing through our waveguide, and some part of the light can be converted to the horizontal polarized, and the overall percentage of the conversion can be also controlled by the length of the optical waveguide. And we also found that this kind of behavior can be extended to a lot of polarization maintenance or manipulation applications. Creating this kind of technology is only the beginning for this project. We have been collaborating with several high-standard research groups across the world that apply this technology into various applications. One of the most exciting things that we have been doing right now is to collaborate with some researchers in Imperial College London that apply this kind of technology into the quantum chips. And there's a huge potential that we can add multiple mode converters to increase the coupling efficiency of the quantum chips. And we're also collaborating with some telecommunication researchers to apply our mode converters into the telecommunication applications. We're also sending the researchers of the polarization manipulation based on our waveguide. There's a huge amount of interesting things that is happening inside the waveguide that we still don't fully understand. But we believe it's going to create a lot of opportunities for us in the future.
It's really rewarding to see how this technology of adaptive optics laser writing can be applied so widely. It's been a wonderful experience to see how we can help others working in other areas of science and technology by creating these new devices enabled through these adaptive laser writing technologies. For example, we are working with people in a wide range of areas, all the way from quantum computation through to imaging for neuroscience. So this broad application is very important to us as engineers to see the wider outside real-world impact of the technologies we have developed.
So it is indeed the first review or perspective that describes the dimensionality that can be achieved by structured light. So we not only summarize several different excellent sub-areas which the great scientists have been done before, as well as we have put forward some perspective on the challenges as well as the chance that we may harness the dimensionality of the structured light that can be achieved. Hope it can make some impact to not only the community, but also for various scientific researchers across the world. especially in the structured light field. This year is very special because it's 30 years of the OEM anniversary, so we are very happy to make the paper online as well as this celebration. So previously, there are already a lot of work which harness the different dimensions of the light beam to do a lot of applications which span across quantum physics to clinical application and even go to materials characterization. So in this work, we not only summarize what people have been done before, but also we give some prospects, especially in the advanced optical communication and or optical data storage, such as go for larger data capacity and higher data flexibility and so on properties. It is worth noting that we emphasize on one very new area which is called optical skymio. This kind of new structured light will be very good. It has very good perspective for the ultra-dense data storage. It can also benefit in many other areas, such like fundamental physics, like the topological photonics, even in some imaging areas, such like harness the skymio beam to be the excitation beam. Then it can benefit the microscope area to do very precise biomedical sensing, biomedical information sensing, or material characterization.